Alright. Um, so, alright, clock is started. Um, kind of some interesting stuff. I was watching a CS Primer video, and Oz was basically talking about that you need to be pretty diligent when it comes to like learning about distributed systems, um, which is basically the concept behind designing data intensive applications. Just because there's not like a real, like it's too encompassing to have like real exercises, and it takes too long to get a feedback loop where it's like I designed a system, I ran a system, and the system failed. So, how do we do it then? He talked about postmortems. Uh, let's see, papers we love. Is this still, do people still contribute to this? Last month, yeah, wow. That's interesting. Oh wow, there's a lot here. Hmm. Hmm. What? Hmm. I'm just clicking through some of these. Mm. Okay, let's get out of here. Oh. Okay, let's see now. I don't want It's not even on the screen, I think. Let me see. No, it's not. Okay. So, what are we doing? Let's think about it for a second. We have some tests to write, but I don't want to get stuck not making any progress. Let's spend like 20 minutes reading, however far that takes me, and then we'll maybe come back to this at the end. So if we come, let's see, storage and retrieval, snowflakes, go back to OBS, move IntelliJ, add Obsidian, boom. Now we're ready. Okay, so stars and snowflakes. Oh, as explored in Chapter 2, a wide range of different data models are used in the realm of transaction processing depending on the needs of the application. On the other hand, in analytics, there's much less diversity of data models. Many data warehouses are used in a fairly formulaic style known as a star schema. The example schema in figure 3.9, let's find that. Okay. Dude, I like cannot focus, dang. Can be found at a grocery retailer. At the center of the schema is a so-called fact table. In this example, it is called fact sales. Each row of the fact table represents an event that occurred at a particular time. Here, each row represents a customer's purchase of a product. If we were analyzing website traffic rather than retail sales, each row might represent a page view or a click by a user, okay? Usually, facts are captured as individual events because this allows maximum flexibility of analysis later. However, this means that the fact table can become extremely large. A big enterprise like Apple, Walmart, or eBay may have tens of petabytes of transaction history in its data warehouse, most of which is in fact tables. Some of the columns in the fact table are attributes such as the price at which the product was sold and the cost of buying it from the supplier, allowing the profit margin to be calculated. Other columns in the fact table are foreign key references to other tables called dimension tables, as each row in the fact table represents an event. The dimension represents the who, what, where, when, how, and why of the event. For example, in figure 3.9, one of the dimensions is the product that was sold. Each row in the dim product table represents one type of product that is for sale, including its stock keeping unit, SKU, description, brand name, category, fact content. Yeah. Each row in the fact sales table uses a foreign key. The product was sold in that particular transaction. For simplicity, if the customer buys several different products at once, they are represented as separate rows in the fact table. The name star schema comes from the fact that when the table relationships are visualized, the fact table is in the middle, surrounded by its dimension tables. The connections to these tables are like the rays of a star. To blow my nose. Me. Um, The variation of this template is known as the snowflake schema, where dimensions are further broken down into subdimensions. For example, there could be separate tables for brands, product categories. Each row could reference the brand category as foreign keys rather than storing them. Snowflake schemas are more normalized than star schemas, but star schemas are often preferred because they're simpler for analysts to work with. In a typical data warehouse, tables are often very wide. Fact tables have over 100 columns, sometimes several hundred. Oh, what? Dimension tables can also be very wide as they include all the metadata that may be relevant for analysis. For example, the dim store table may include details of which services are offered at each store, whether it has an in-store bakery, the square footage, the date when the store was first opened, when it was last remodeled, how far, yeah. Alright, Um, so uh, to dimension tables. So it's this is funny. So it's literally talking about um, column compression, right? But this is actually the earlier uh, concept of normalization, right? So listen to this. Uh, so take a look at the sequence of values for each column in Figure 310. They often look quite repetitive, which is good, which is a good sign for compression. Depending on the data in the column, different compression techniques can be used. One technique is particularly effective with data warehouse is bitmap encoding. So the number of distinct values in a column is small compared to the number of rows. For example, a retailer may have billions of sales transactions, but only 100,000 distinct products, right? We can now take a column with n distinct values uh, and turn it into n separate bitmaps, one bitmap for each distinct value, with 1 bit for each row. The bit is 1 if the row has that value and 0 if not. The bit is 1. Okay, I don't know what it's talking about, but basically they make a map of the values, right? I think that's what they're talking about. And then you would only ever store 100,000 values, and then you would store a reference to that value, right? Hmm. Hmm. feel like I don't really understand how it works, and I'm afraid ChatGPT is gonna give me the wrong thing. Bitmap indexes, I'm on Wikipedia, work well for low cardinality. Cardinality is a set. Cardinality of a set is the number of its elements. So yeah, that's what it said too. The less elements, the better. The better it's going to work, I should say. Which have a modest number of distinct values. Yeah. Bitmap indexes use bit arrays and commonly called bitmaps. Okay, so we're just bitmap index or bit array index, and answer queries by performing bitwise logical operations on these bitmaps. Bitmaps indexes have significant space for performance advantage. Yeah. Some research indexes are useful model or even high cardinality data, which is accessed in a read-only manner and queries accessible. Okay. Okay. 10 minutes left. So one example here is that a country, so it's a column that might have 200 distinct values. Those bitmaps can be stored with 1 bit per row, but if n is bigger, there will be a lot of zeros. So I think the idea. No, I. Okay. So I think it's like this. You have an array of IDs, so 1, 2, 3, 4, 5 IDs, and then you have country, so USA, China, Russia, and that's fine. So then the bitmap, right? It's either 0 or 1. And we'll say this ID is in. Why is this off? Are you serious right now? That's so annoying. Okay, that's better. 0. So 0, 0, 1, 0. And now you know that you can look at the USA column. So if I query for all records that have USA country in it, I can look at this array and literally grab the IDs from this array. I think that's what it's trying to talk about. And if you wanted USA and China now, you can use the AND bitwise operator to combine these two, and then you grab the IDs because they're the same index, right? Got it. Yeah. So now you can also see why the number of unique values is important. So you would have around 200 rows for countries, but if you had 100,000 unique values, you would have 100,000 bitwise maps. Got it. Okay. Got it. So that's a little better. 7 minutes left. All right, let's pause here. Let's do. Can I type? Dude, I literally cannot type. My brain is shutting down. All right, well, I'm done here. Cool. How much further do I have? 1, 2, 1, 2, 3, 4. 4 more pages. I'll finish it next time. Cool. And then we'll be on to the next chapter. Cool. Okay, I don't have a lot of time. Oh, when there's 18 cards, we better get through some of them. What are the downsides of imperative queries embedded in application code? So this is when you have like joins written in code rather than in declarative SQL. And the downside is like it's prone to errors, tightly coupled, like with application logic and business logic. I feel like there's something else and I can't remember. More prone to errors. Oh, harder to optimize. That's right. Okay. What is the graph data model best suited for social networks, recommendation engines? Yeah. Network topologies. That's a cop-out. It's a grudge, bro. When is the document model a better choice than the relational model? When your data looks like a document, when you need data locality, and when you can tolerate duplication. Tolerate schema flexibility. I forgot that one. A declarative language is one where you tell the computer exactly what to do and what steps to do. Fuck. I keep messing that up, dude. Okay. Declarative is when you describe a pattern and this application decides how to provide it. You say what, it says how. Yeah. Declarative is you say what, it says how. Dang, bro. I missed that one a few times. I think I'd get it by now. What is the benefit of declarative query languages like SQL? It's an abstraction, so people can write optimizations for queries that can benefit everyone. Simplifies the logic. You know. MapReduce is a programming paradigm that you can run on large data sets of distributed systems. So think snippets of code run on each piece of data. Processing large amounts of data in bulk across many machines. Okay. A heap file is a file where data is stored in no particular order and lookups are by offset. Why is this useful? You can use up more memory because it can just be contiguous since you're just using offsets rather than I'm just gonna stop. No particular order, common approach because it avoids duplicating data. Sorted string table, and it's a mem cache that will eventually be turned into a segment file. A log file that is sorted by key, short for shorted string, differs from an append only log file. This is such a weak definition, right? A covered index is an index that partially stores the data with the index. Nice. B trees or balanced trees are a way, it's different than let's finish this one. It's different than SS tables, they're balanced trees, and a B tree represents a range of keys, and each value will either be data or a reference to a leaf node, and the entry point is the root. Always balanced, takes O of log n, work has fixed size, have a root page and leaf node. So I'll say 8 days. I'll say this one was hard because I missed a few. Okay. I'm out of here. Cool.